Have you ever looked up at a solar panel and just wondered what is actually going on in there? How does this silent slab of glass and metal turn pure sunlight into the electricity that powers our lives? Well, today, we're going to break it all down. Okay, let's dive right in. So to really get this, we've got to start with the sheer scale of it all. Every single moment, the sun is just bathing our planet in an incredible amount of energy. We're talking 174 petawatts hitting the top of our atmosphere. That's 174 with 15 zeros after it. It's more energy than all of humanity uses in an entire year, delivered constantly for free. The potential is it's immense, almost limitless. But tapping into it, that takes a little bit of clever physics and some really smart engineering. The key lies in this remarkable invention, the photovoltaic cell. At the heart of every single solar panel is something you can pretty much think of as a silicon sandwich. Now, this isn't just a random chunk of material. It's a precisely engineered engine with absolutely no moving parts, and it's designed to do one thing perfectly: capture light.
The main ingredient here is silicon. You find it everywhere. It makes up over a quarter of the Earth's crust. But what makes silicon so special is that it's a semiconductor. It's not quite a conductor like copper, and it's not an insulator like rubber. It's somewhere in the middle, and its ability to conduct electricity can be tweaked. That right there is the secret to everything. So, to build our engine, we take pure silicon and we dope it, which is just a fancy word for mixing in tiny amounts of other elements. For one layer, we add phosphorus, which brings an extra electron to the party. This creates what we call N-type silicon, for negative. For the other layer, we add boron, which is actually missing an electron. This creates P-type silicon, for positive, and it's full of these little electron vacancies we call holes.
Okay, so this idea of a hole can sound a little weird. It's not actually empty space. Think of it more like a reserved parking spot in the crystal structure where an electron should be. And because an electron is missing, this spot has a positive charge, creating this powerful attraction for any electrons nearby.
And this is where it gets really brilliant. The holes themselves seem to move. An electron from a neighbor gets pulled into a hole, right? But in doing that, it leaves a new hole where it used to be. It's just like one of those little sliding tile puzzles. The electrons move one way, and the empty space, the hole, appears to move in the exact opposite direction.
So here's the magic moment. What happens when you press these two layers together? Well, the free electrons from the N side immediately rush over to fill the holes on the P side. This creates a barrier right at the junction, and that barrier sets up a permanent electric field. This field, called a p-n junction, acts like a one-way gate, and it stops any more electrons from crossing back. This little gate is the key.
All right, so we've built our silicon sandwich, we've got our one-way gate. Now we just need a spark, a little push to get things going. And that spark comes from the sun, in the form of a photon.
Now, this whole process has a name, the photovoltaic effect. And get this, it is not a new idea. The French physicist Edmond Becquerel first spotted this phenomenon way back in 1839. He noticed that one of his electrodes, when hit by light, produced a small electric current.
So here's how it all goes down. A photon, this tiny packet of light energy, comes flying in and slams into a silicon atom. If it has enough energy, it knocks an electron right out of its spot, creating a free electron and a new hole. Now remember that electric field at our p-n junction? It's like a bouncer at a club. It immediately grabs this new pair, shoves the electron over to the N side, and pushes the hole over to the P side. No exceptions.
This forced separation is the whole point. With all the negative electrons piling up on one side and all the positive holes on the other, the cell now has an electrical potential. It has a voltage. And just like that, in that instant, we've turned pure sunlight directly into electricity.
But the voltage from one tiny cell isn't enough to be all that useful. To power anything significant, we've got to think bigger. We need to scale up.
So manufacturers wire dozens of these individual cells together in series, positive to negative, just like stacking batteries. This combines all their voltages into something powerful enough to be practical. Now here's a crucial point. All this power is in the form of direct current, or DC. Your home, your appliances, the entire grid, they run on alternating current, AC. So every solar system has an unsung hero, the inverter. Its only job is to take that raw DC power from the panels and convert it into the AC power that actually runs our world.
This whole series connection thing, though, it creates a potential weakness. In a series circuit, the current has to be the same through every single component. So
What happens if a leaf or a shadow blocks the light to just one of those cells?
Well, that one shaded cell stops producing power. It can't generate any current, and because it's part of the series, it becomes a roadblock, a bottleneck. The current from all the other working cells tries to force its way through, causing that shaded cell to heat up like crazy. This is called a hotspot, and it can permanently damage the panel. So this solution is another piece of really clever engineering, the bypass diode. Instead of one long series, the panel is broken into smaller groups of cells. Each group has a diode wired up with it. Now, if one section gets shaded and the current gets blocked, the diode provides an alternate route, a bypass. The current just flows around the non-producing section, allowing the rest of the panel to keep working without creating a dangerous hotspot.
So we've gone from a single photon all the way to a full panel. But how good can this technology actually get? Are there limits? And what's next?
Believe it or not, there's a hard physical limit to how efficient a standard silicon solar cell can possibly be. It's called the Shockley-Queisser limit. It basically accounts for the fact that some photons don't have enough energy to knock an electron loose, while others have way too much energy, which just gets wasted as heat. For a single p-n junction made of silicon, that absolute max efficiency is about 33.7%.
To push past that limit, researchers are exploring entirely new materials. We're all familiar with the solid gray silicon wafer, but what you're looking at here is the crystal structure of something called a perovskite, and right now, it's one of the most exciting materials in solar research today.
So why is everyone so excited? Well, perovskites can be made cheaply, using low-temperature processes. You can almost print them like ink. This opens the door for flexible, lightweight, and even semi-transparent solar cells that you could build into windows or fabrics. And their efficiency has been skyrocketing in labs, improving faster than any other solar technology in history.
When you put all of these pieces together, the fundamental physics, the clever engineering, and all this cutting-edge research, you get a really powerful vision for the future.
It's amazing to think about. The journey of a single, massless photon traveling 93 million miles from the sun ends by setting off this chain reaction in a slice of engineered sand that ultimately powers our homes and our world. It really is a quiet miracle of physics at work all around us.
And this technology is only getting better, more efficient, and more accessible. It's a constant reminder that the solution to many of our energy needs isn't buried deep underground, but is shining down on us every single day.